Hello, my name is Dartnell. I'm a professor at the University of Westminster and I'm an astrobiologist. I'm interested in the possibility of there being life beyond the Earth, whether we might find simple bacterial-like organisms on the surface of Mars, for example. What I'm talking to you guys about today, though, is how we can explore our solar system and outer space, not with our eyes, not peering down a microscope, but how we could use our ears to explore what the sounds of the cosmos really sound like. Now, of course, if you were to actually go out into outer space and accidentally take off your space helmet, you would die. You would die very, very quickly because there's no air in outer space. There's no oxygen for you to breathe. And even if you were to scream as hard as you possibly could, no one would be able to hear any sound because there's no air to move those sound waves around. But that doesn't mean that we can't hear sounds from outer space. Other kinds of waves can travel through outer space, like radio waves. So we'll listen to some recordings of radio waves being played through our speakers, but there are also some examples of genuine sound waves from things beyond our Earth. So for this tour, we're going to start on the surface of the Earth, travel out through the solar system, and then across the cosmos as a whole, stopping off on different places along the way and listening to what they actually sound like. First on our tour of the solar system are what shooting stars or meteors actually sound like. These are tiny little grains of rock or space dust moving at incredible speeds. So when they slam into our upper atmosphere, they heat up and get destroyed in this bright streak of light. And that's what we call a shooting star. Now, if you've got a radio antenna on the surface of the Earth and you're pointing it up at the sky, you can hear reflections from those trails behind the shooting stars coming back at you as radio waves. It's almost like hearing the echoes of the radio. And the first recording we're going to listen to are these little blips of these echoes coming back from shooting stars. Now, see if you can listen very carefully and count how many shooting stars you can hear in this radio recording. That background tone is just the radio signal. And that beep there, that's one shooting star. There's another one. Shooting stars aren't the only things that we can hear if we had radio ears. And every time there is a thunderstorm and bright flashes of lightning, like in the picture here, these shoot up electricity. They shoot up electrons high up into the upper atmosphere where they can start bouncing back and forth in Earth's magnetic field. And they give off radio waves again when they are bouncing around the magnetic field. So again, if you've got a radio antenna, you can hear the radio waves being given off by thunderstorms like this. And the recording that I've got for you of these whistlers, as they're called, is a brilliant recording where researchers have got a radio mast in California on the left of the map here, and they've got another radio mast in Colorado just outside Denver, and they're recording almost exactly like having left and right radio ears that have been stretched out over 1,000 kilometers apart. So if you close your eyes while you're listening to this recording, it'll really help your imagination hear that stereo sound effect of these whistlers from thunderstorms happening right across North America. Here we go. Each of those little pings is another lightning flash somewhere in North America. The aurora, the northern and southern lights, are incredibly beautiful visual displays, but you can also hear them as well if you can listen to radio waves. The aurora are created by the solar wind, which is a stream of particles constantly blowing out from the surface of our sun across the solar system and then meeting our planet. And the magnetic field around the Earth helps channel and funnel those solar wind particles down into the atmosphere over the north and south pole. So that's why the aurora are called the northern lights and the southern lights. You can also see the northern lights not stood on the surface of the Earth looking up, but if you're in outer space looking down. This image here is taken by an astronaut looking out the window on the International Space Station at these beautiful shimmering curtains of green light high up in Earth's atmosphere. These are the aurora. And if you were to tune the radio set on board the International Space Station to the right frequency, you'd be able to hear what those aurora sound like as well as they give off radio emissions. This sound effect can be a little unpleasant. So although the northern and southern lights on the Earth may look very beautiful, I'm not entirely convinced I'd really want to listen to them, listen to those radio emissions for very long. I've got another recording for you. This actually is a recording of sound waves in outer space. This is a recording from a microphone on board the International Space Station. And I want you to see if you can hear the astronauts in the background as they're going about their day-to-day lives on board the space station. It's actually really noisy on board the space station, rather than on the Earth, when there's the air that you can breathe, or water that you can drink. When you're living inside the space station, this little metal bubble that's trying to keep you alive, everything that goes on around you is mechanical or electronic. It hums or it buzzes. And so the space station is actually a very noisy place to try to live. Astronauts can often have a lot of trouble trying to get to sleep with all that constant background din going on around them. And as you can maybe also see in this photograph here, ironically, on the space station, there's hardly any space. It's all incredibly cramped and claustrophobic when you're living inside this little tin can high above the Earth in orbit. Now on our tour of the solar system, we're going to move beyond the Earth and travel to the very center of our solar system, where the sun, our local star, is found. And the recording I've got for you was made by a spacecraft, a probe called the Solar and Heliosphere Observatory, or SOHO for short. And SOHO, with its telescope and outer space, was able to observe very, very accurately the surface of the sun as it wobbled up and down with all of the churning and turbulence going on beneath the face of our local star. And these are genuinely sound waves. These are vibrations on the surface of our sun. And if you speed up those recorded vibrations from the SOHO spacecraft about 40,000 times, you can then hear what our sun sounds like. This is almost like the song that our sun is singing as it buzzes and vibrates. The first recording I've got for you here is the bass note of almost like the heartbeat of the sun. It's primary vibration. And these waves have got a period of about 5 minutes, so very, very slow compared to the sound waves that we can normally hear. And then after you've heard that bass note of the sun, we'll hear all of the different vibrations being played on top of each other all at the same time. So that background hum you can hear is this very regular vibration of the surface of our sun. It's sound waves rippling across the face of the star. And now the slightly more complex sound is all of the different vibrations on the surface of the sun all being played at the same time. But you can still hear that background note, that fundamental frequency that our sun vibrates with. Now, travelling beyond the sun at the centre of the solar system, back past the Earth where we started, we come to our next door neighbour planet, Mars. This is one of the planets that I spend most of my time thinking about as an astrobiologist. And very, very excitingly, just a few weeks ago, the latest NASA rover touched down on the surface of Mars. The Perseverance rover dangled beneath its sky crane and was safely delivered to the surface of the red planet. And amazingly, the Perseverance rover has got a microphone on board. What I'm about to play to you is a genuine microphone recording of what the surface of another world sounds like. Most of the background hum is the vibrations and the motors on board the rover, but a couple of seconds into the recording, you can very distinctly hear a Martian breeze, a Martian wind blowing over that microphone. That is one of my favourite recordings out of all of them I've got to play for you today. It blows my mind thinking about this robot explorer on the surface of Mars actually hearing the wind blowing around it. Now we travel beyond Mars, through the asteroid belt. The next planet we get to is Jupiter. And Jupiter has aurora, has northern and southern lights just the same way that we do on the Earth. Jupiter also has a magnetic field. It also funnels a lot of particles down into its atmosphere to generate those northern lights, and they also give off radio emissions at the same time. So we're now about to listen to the whistles coming from the northern lights in the magnetic field and the atmosphere of Jupiter. You can hear those really distinctive whistling sounds, starting at quite a high note and then descending down again. Let's have another listen to that recording. It's quite a short one. Moving past Jupiter, we get to Saturn, one of my favourite planets, the magnificent Lord of the Rings, with this glorious ring system around the planet. And we've got to know Saturn very well as a planet because we've been exploring it with a space probe called Cassini. Now, when Cassini first arrived at Saturn in the year 2004, it had been travelling through space for about 7 years after we launched it from the Earth, and it had to fire a great big rocket to slow down and get captured by the gravitational pull of Saturn and fall into orbit like a satellite around Saturn. And one of the problems with Saturn, if you're trying to fall into orbit like a probe, you have to get quite close to the rings of Saturn. You have to pass through them. And the rings of Saturn, although they look very beautiful, are a pretty dangerous place to be as a space probe because they're made up of lots of chunks and shards of water ice. That's why the rings of Saturn glitter so beautifully. So in order to pilot the Cassini space probe as safely as possible, the mission designers flew it straight through the gap you can see in the middle of the rings of Saturn there. It's called the Cassini division. But even in this gap, there's still a few little flecks of ice drifting around. And the recording I've got for you is a recording made by the Cassini space probe as it flew through the rings of Saturn, and it picked up every little impact from those ice crystals in the rings of Saturn. This recording, again, it blows my mind when you think about what you're actually listening to. This sounds just like the pitter-patter of rain on your car windscreen if you're driving through the rain. But what we're actually listening to are the pitter-patter of the ice crystals of the rings of Saturn against the Cassini space probe when it passed through as it first arrived. Have a listen to this. Saturn has rings, and also it has aurora, just like the Earth, just like Jupiter that we've listened to already. But as far as I'm concerned, the aurora on Saturn sound exactly what space should really sound like. This sounds to me like the background score, the sound effects to some kind of science fiction film. So have a listen now, maybe close your eyes and listen to this one nice and carefully, because this is what the magnetic field and the aurora on Saturn sound like from their radio emissions. Now, as well as lots of rings, Saturn also has lots of moons orbiting it. And in fact, Saturn has got the largest moon in the solar system around it, a moon called Titan. Now, Titan is a moon that's even bigger than the planet Mercury. It's a giant moon, and it's a moon that is absolutely covered in haze. It is a moon that has an atmosphere, that has air around it. And in order to explore the moon of Titan, we sent a very special kind of space probe to explore it. Attached to the Cassini mission we mentioned earlier was a descent probe called Huygens, a probe that had a parachute so it could sink gently down through the hazy, cloudy atmosphere of Titan and send us back some photographs of what the Titanic landscape looked like. The first recording I've got for you of this incredibly bold mission of Huygens is the descent radar aboard this probe. So it could work out how high above the surface it was as it descended underneath its parachute. It had a radar system that bounced off radar signals off the ground as it sunk lower and lower. So what we're going to listen to is going to be quite an electronic-y, computery sound effect. And these beeps from the radio pulses will get quicker and quicker and quicker, faster and faster, as Huygens gets closer and closer to the ground until eventually it splashes in this squelchy impact onto the sodden surface of Titan. So there's this very computer-like sound effect of the radar system that's now locked on to the surface of Titan. And it's starting to sound a little bit like a space motorbike. Each of those blips, they're getting faster and faster and faster and closer together, is another radar pulse from the Huygens lander as it gets closer and closer to the Titanic surface as it descends beneath its parachute. Bloop! I love that ending to that recording when Huygens eventually squelches down onto the surface of Titan. Now, like the Perseverance rover that landed very, very recently on Mars, Huygens also had a microphone on board, and we can listen to the Titanic winds buffeting this probe as it parachutes down onto the moon of Titan. This is the second recording I've got for you here. So this is almost exactly like if you're on your mobile phone trying to have a call with your mum or your dad or your friend, and the wind is blowing across the microphone. People find it quite hard to hear what you're saying because it's just over the microphone. Well, this is what we're listening to, but from a wind on another world. The Titanic winds on the giant moon that orbits Saturn. Now, moving right across the solar system towards the very edge of our solar system, where the influence of the sun meets the interstellar space. And we've sent a couple of probes even this far to the edge of the solar system. And the recording we're about to listen to here was made by Voyager 2 probe, and it's listening to the radio emissions coming from the very edge of the solar system, from the outside bubble of this termination shock. This is a very short recording, so listen very carefully, and you'll hear a couple of blips coming back from the very edge of the solar system. Now, we've listened to what the song of our sun sounds like. We listened to the vibrations and the sound waves rippling across the face of our sun. We've also been able to do the same sort of measurements on the surface of other stars as well, including this star, Xi Higher, which is a star which is much, much bigger than our sun. It's about 10 times wider. And so the vibrations on the surface of this star, just like the vibrations on the skin of a drum, are much deeper, much lower than the vibrations on our sun. But you can still hear this really distinctive rhythm in the vibrations in this star. Can you hear that? That's almost like music, that rhythm, that beat, the heartbeat of this sun. Now, when stars like Xi Higher reach the end of their lives, when they run out of nuclear fuel in their core, they die in the most spectacular, catastrophic explosion called a supernova. They blow themselves completely apart, and all the outside layers of this star are thrown out into interstellar space. And what gets left behind when these massive stars undergo supernovae is the heart, the very core of that star has been compressed down into a very special kind of object known as a pulsar. Now, a pulsar is an exotic kind of object in the universe where it has a very, very powerful magnetic field, and it beams out radio waves from its north and south pole in these two bright beams of radio waves. And as that star turns round, those beams of radio waves sweep across space, just like a lighthouse with two beams of light turning round sweeps across the coast or out across the sea. So if you have a radio antenna that can listen to those radio waves, as that pulsar spins round and round, you hear a blip, 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 blip of radio waves. Have a listen to what I mean. So this is a very, very regular beating of radio waves from this pulsar. It's almost like a great big metronome in outer space, keeping very precise timing. This particular pulsar has got the very boring name of PSR B0329 54. That's basically just a catalogue number. That's how astronomers know which pulsar they're talking about. Now, because pulsars are formed from different stars that explode in different ways, each pulsar spins at a slightly different rate. So the clicks that you can hear from its radio emissions come with a particular rhythm. And the next pulsar we've got to listen to is from the Vela supernova remnant. This star exploded around about 10,000 years ago. So around the time that humans had been migrating around the world from our cradle in East Africa and were starting to settle down and invent agriculture and farming and civilization, this massive star exploded as a supernova and left behind a pulsar. And this pulsar spins a little more quickly than the last one we heard, so its ticks come a bit faster. This Vela supernova remnant is spinning 11 times every single second. It's incredibly quick for something the size of a pulsar. And they can get even faster than that. This supernova here created the Crab Nebula. It's visible with even a relatively small telescope. And this star exploded in the year 1054. It was noted, it was recorded by astronomers in Europe and China about 1,000 years ago. And the supernova that's been left behind, sorry, the pulsar that's been left behind by the supernova spins even faster. This is spinning about 30 times every single second. Now this pulsar is starting to sound almost like a pneumatic drill or maybe some kind of like car engine in outer space because it's spinning so quickly and those radio pulses are coming so fast on top of each other. Now the last pulsar recording I've got to play for you is from a pulsar that is spinning so quickly. It's rotating over 640 times every single second. So the human ear can't even hear the difference between each of those radio pulses. They smear together, and all we end up hearing is a very high-pitched note. This pulsar in radio waves sounds almost like some kind of space mosquito. And again, this sound isn't entirely pleasant to have to listen to. This is a little bit of a grating sound of the cosmos. That is quite enough of that, I think. Now, stars often form in great big clouds, great big swarms of stars known as a globular cluster. And they're all orbiting and swirling around each other, almost like a swarm of bees, but made up of stars in outer space. And when those more massive stars in this swarm explode as a supernova and leaves behind a pulsar, it has a pulsar with a particular rate of ticking. The pulsar has a particular speed that it spins with. So if you've got your radio telescope and you point it towards a globular cluster like this and move around ever so slightly, you can pick up one pulsar and then another and then another and another, each spinning with their own particular rate and each sounding like they've got their own particular note, depending on how quickly they're spinning. So this recording sounds almost musical at the beginning as we hear one note after another from these radio emissions from the pulsars in this globular cluster. And at the end of the recording, they're played all at the same time in this horrible cacophony of pulsar notes. And there's that cacophony of notes right at the end as this orchestra of the pulsars inside this globular swarm are all tuned into at the same time. Now, the very last recording I've got for you on our audio tour of the universe takes us all the way to a supermassive black hole. And this black hole is 250 million light years away. It's far beyond our galaxy. It's the black hole in the center of another galaxy in the Perseus galaxy cluster. And what you can just about make out in this telescope view of the black hole in the center of this galaxy are ripples moving out in the gas in outer space. There are ripples moving through that gas that have been created by the activity of the black hole right in the center. And if you have ripples moving through a gas, even if it's incredibly thin gas, like in outer space, that is a genuine sound wave. That's no different in terms of the physics to what's going on in the sound in Earth's atmosphere. So though we don't have an actual recording of this black hole, we can measure the distance between each of those sound waves. We can calculate what note it corresponds to, and it turns out that it's actually a B flat. The sound waves rippling out from this supermassive black hole in this galaxy has a note that corresponds to B flat, although it is a very, very low note. It's something like 1,000,000 billion times lower than the lowest sound the human ear could ever detect. That's about 57 octaves below middle C. So the recording I've got for you is a recreation of a very low B flat. To just be able to make out that really deep bassy sound that corresponds to the sound waves emanating out from this black hole in the center of the galaxy in the Perseus galaxy cluster. Now that's the end of our tour of the sounds of the cosmos. I've been Lewis Dartnell, and as well as doing a lot of research in astrobiology and doing talks like these about different aspects of science, I do a lot of writing as well. And each of my 4 books that you can see here are all available as audiobooks as well. Look them up on an online bookshop or download them wherever you get your audiobooks or podcasts from. But thank you ever so much for listening to me, and I hope you enjoyed our tour of the solar system. Cheers.